Welcome back. Hope you're doing well. Last time we were discussing orthogonality in Rn. We were especially using the dot product as our way of working through vector spaces that were in more of a familiar format than what we had had previously. Instead of looking at abstract vector spaces, we were using Rn as a launching point for us. But of course, whenever we start these things looking at launching points, we want to keep trying to generalize the things that we're doing. That's a goal for us this entire semester, is to take the things that we know in Rn, concretize them, and use those as intuition for any other types of inner product spaces, like the ones that we've seen. Recalling ones like the function spaces that we've seen before, remember that we said that there were ways to take continuous functions going from A to B and write an inner product for these two things. Namely, we would say take these two functions here, f and g, and if these were, say, going into the real numbers, we could just say that this is the integral of f of x times g of x dx. And if these were going into the complex numbers instead, then the only thing that we would be adding is a little bit of a bar over the g of x. So we've talked about how the inner products differ for real and complex numbers and how this can give us an example of an inner product on this space. So we're going to be looking at some function spaces here as well, and we'll be doing that later on in this section. But let's make sure that we get our definition straight for any general inner product space. Again, when we say inner product space, we're starting with a vector space, and we're saying that there exists an inner product that works on that space. So it's an inner product space, it's a vector space itself, and it's an inner product. In general, it's an abstract vector space, not necessarily Rn. So we'll say that two vectors x and y are orthogonal if their inner product between them is 0. I would be tempted to say dot product here, but since I don't quite know what a dot product would mean in an abstract vector space, I'm going to say inner product here instead. The inner product between x and y. For example, the dot product is the inner product in Rn. We could also say that a vector is orthogonal to a non-empty set if whenever you take an element inside of that set and take its inner product with the vector, you get 0. So that is the same definition as before, now in a more general context. And then finally, if you have two non-empty sets, say x and y, and you take an element in x and an element in y, and regardless of your choices on the left and on the right, their dot product or inner product, excuse me, is 0, then you would say that those two sets are orthogonal. So that is the notions of inner product for these general inner product spaces. Now, orthogonal sets are interesting for us, and they're going to have the same sorts of contexts that we saw here in the real numbers. A way to be thinking about these is that even if we're working in an infinite dimensional vector space, there is still a notion of perpendicularity between these two things. And so a lot of our intuition behind that is going to come from that. We're going to take a set, not a subspace, just a set of elements inside of our vector space. And we're going to say that that set is orthogonal if all vectors in that set are mutually orthogonal. By mutually orthogonal here, I mean kind of like pairwise. If you take any pair of elements inside of a set S and take their inner product, you get 0. Of course, we cannot have the pair be a duplicate. We cannot have x and x both be chosen because, namely, we wouldn't want a bunch of 0 vectors at the end of the day. So we're going to say whenever x is not equal to y, the inner product of x and y is 0. We're going to add another definition to this too. Orthogonal sets are interesting to us. For example, in terms of R3, we've got 1, 0, 0 and 0, 2, 0. These two vectors are orthogonal to each other, and together they would form an orthogonal set. Notice that they do not have to be a basis for this set, and neither do they have to be unit vectors to be an orthogonal set. Now, if they do end up all being unit vectors, which in an abstract sense means that they have a norm or a length of 1, then we're going to say that orthogonal set is orthonormal. Orthonormal here means they're standardized to some extent. These are standardized to be all of the same length, and that length is 1. So an orthogonal set would be something like this, whereas if we were to make this an orthonormal set, we would be looking at 1, 0, 0 and 0, 1, 0. Notice that this is an orthonormal set and not an orthonormal basis. We may remember this from linear algebra days, perhaps, or for some other sort of context, but an orthonormal set is one step away from an orthonormal basis, which we have not yet defined. So we have orthogonal set, orthonormal set, and those are the two things that we are analyzing here. Now, the vectors v1 through vk end up forming an orthonormal set if and only if we can just check the inner products of these individual vectors themselves and ask the question, what does it mean to be an orthonormal set? Well, it turns out that you can write it as one little slick, neat function. Well, if you have two different vectors, we know that their inner product has to be 0, so we've gone ahead and written that down. But what happens if you have the inner product of the vector with itself? If it's orthonormal, then because the length of the vectors are 1, and the length is defined in terms of the inner product, square root of the inner product, that is, then we know that the inner product has to be exactly 1 whenever you're taking the inner product of the vector with itself. So this is the example of vi, comma, vi, when these two are the same vectors inside of our space. Okay, so this gives us orthogonal and orthonormal set definitions. In Rn, we've got our standard basis, which forms an orthonormal set. You remember that these are all what we would call unit vectors inside of Rn, and that a dot product is our inner product. With all of this stuff in tow, this gives us an orthonormal set. But we don't have to consider just this. We could consider other vectors here as well, like v1, v2, v3 given here. v1 being 3, 5, 4, v2 being 3, negative 5, 4, and v3 being 4, 0, negative 3. Now, it might be a little bit hard to believe, but if you take the dot product of any of these two vectors pairwise, then you end up getting 0. You end up getting 0 for that dot product. For example, 3 times 3 plus 5 times negative 5 plus 4 times 4. That's 3 minus 20, or 9 minus 25 plus 16. That gives us 0. And we can do the same thing for each of these other pairs here as well. Now we take the dot product of v1 with itself, v2 with itself, v3 with itself to see if this set, which we've already shown to be orthogonal, is also orthonormal. Remember that orthonormal would mean that each of these vectors is of length 1. However, these vectors are definitely not of length 1. You can see here that the dot product of v1 with itself is 50, as is the dot product of v2 with itself, and the dot product of v3 with itself is 25. So v3 is a length 5 vector. Now, how can I take v3 and make it a length 1 vector? What I could do is I could just take v3, and since it's a length 5 vector, I can divide it by 5. Namely, I can divide it by the length of the vector given there. So even if I'm just given a set that is orthogonal but not orthonormal, I can still form an orthonormal set by normalizing each of the vectors. So I could take the norm of each of those and divide it by its respective norm. So if I have an orthogonal set, I can get it to be orthonormal. It just goes through and says, okay, we can write these 3 vectors out and get something there. So just normalizing them so that each of them have length 1. Now, we could be looking in terms of functional vector spaces as well. Let's take the space to be the space of continuous functions going from negative pi to pi. That means these functions start at negative pi and they end at pi. Well, why are we choosing these endpoints? Because we're looking at sine of x. These are the functions that look like this. All right, and because of that, sine of 2x is going to speed up its period, so that will look a little bit like this. And then in general, we're going to be adding one more to this number inside of here. We'll start with something that has a period of 2 pi, then we're going to get something that has a period of pi, then something that has a period of 2 pi over 3, and so on and so forth. And the question that we can ask is, what is the relationship between each of these functions whenever we take their inner product? For example, let's take the inner product of sine x and sine of 2x. And let's ask, what does this end up becoming? Well, the integral of sine of x times sine of 2x. We know that sine of 2x can be written using a double angle formula as 2 sine x cosine of x. So when I integrate this going from negative pi to pi, I can write this integral as, this is f1 comma f2. I can write this as 2 times sine squared of x cosine of x. There's a u substitution to be done here. U equals sine of x, so du is cosine of x, and that divides away. And I'm left with 1/3 times sine cubed of x going from negative pi to pi. Now, sine is 0 at both negative pi and pi, so sine cubed of x will be 0 at negative pi and pi. This integral should evaluate to be 0. And it should indeed be 0 for anything else any other combination of f1, f2 through fn. If I had done not f1 and f2, but f2 and f5, then the formula should have been the same. All right, and this takes a little bit of time to get through, but we could potentially do this with enough double angle formulas or some difference trigonometric formulas. And once we get through all of that, we realize that the inner product of these two things is 0 whenever m is not equal to n. Now, on the other hand, if I take the inner product of one of these with itself, like for example, the integral of sine squared of x, then I know that I can use a double angle formula to write this as something like, say, 1 minus cosine of 2x over 2. That one integrates. That one integrates to pi. Integrates to pi whenever you have the inner product with f1 with itself. Now, that's the same thing, it turns out, whenever you have f2, as well as when you have f3, f4, and so on and so forth. So this gives us an orthogonal set. The set of sine x, sine of 2x, sine of nx, all of these put together, gives us an orthogonal set. Now, it's not orthonormal because we notice that if we take the inner product of any element with itself, it ends up being, has a length of pi, right? And literally, we can think of it that way. It has a norm or a length of pi in terms of this inner product. Now, how can we make it orthonormal? We have two choices. We could either take each set here, right, each function, and divide it by maybe square root of pi, right, something like this. Maybe better to say, let me just check and make sure in my head that that works. Maybe instead we would actually just, I think dividing by pi, nope, yeah, dividing by square root of pi on each of those functions, I had to do the math in my head, should get us to where we need to be because we get to factor out a 1 over square root of pi with each of those functions. And then when that integrates to be pi, we get to divide by pi and get 1 before taking the square root of that inner product to get the norm. But we could also do something else. We could also scale the inner product itself to get one that is slightly different. Notice here that we have written a slightly different bracket notation, this time multiplying times 1 over pi. This is a scaled inner product. Notice that this is the same inner product as the one we were given, but every inner product is multiplied by 1 over pi. This turns out to be an inner product as well. It satisfies all of the conditions of its definition. It's still linear. It still is non-zero, except when the vector is 0. When you're taking inner products to that vector with itself. So it satisfies all of our conditions for what an inner product should be. And now notice whenever I take the inner product of a vector with itself, namely a function among this orthogonal set with itself, then I get that this should evaluate to be pi over pi, which is going to give me 1. So that's another way that we could be finding this to be an orthonormal set. We could change our functions, or we could change our inner product. In terms of looking at continuous functions, instead of going into the real numbers in terms of complex numbers, we end up looking at things that are slightly different. We might look at, again, recall that our inner product here is going to be not f of x g of x, but f of x g of x bar, that is the conjugate of functions in g of x. And we might also notice that this inner product is already pre-scaled, if you will, for us, this time divided by 2 pi, thanks to our new set of functions that we're going to be looking at. The functions that we're going to be looking at are trigonometric functions, but they look a little funky. These functions are going to be called h sub n of x, which is equal to e to the I n x. E to the I n x. So for example, h1 of x is just going to be e to the ix. Remember that we can rewrite this. We could write this as e, or not e, but cosine of x plus I sine of x. And then if we had I times 2x, then for h2 of x, for example, we would have that this is equal to cosine of 2x plus I sine of 2x. And now we start realizing that there's a little bit of similarity between these functions and the ones that we had in the previous vector space, the ones where our functions went into the reals, whereas these go into the complex. Namely, if I just isolated the imaginary parts of each of these, I would have the same orthogonal set as what I had before. And on the real coordinate line, we have now the functions cosine of x, cosine of 2x, and so on and so forth. Now, it still remains to be seen what actually happens when I try and do the inner product stuff with this stuff. So let's see what happens when I try and take the inner product of these two things together. Well, what's going to happen is this. Let's say that I have hm and hn, these being either the different or the same element inside of this orthogonal set. And I'm going to take their inner product. Here's e to the I mx. Here is the bar of e to the I nx. Now, you've gone ahead and evaluated what that would look like. It's going to be e to the negative I nx, which means that it's easy to combine these together like this. We're going to have e to the I times m minus nx here. And something interesting happens if m and n are equal. If m and n are equal, then this is equal to 0, which means I'm just integrating e to the 0. This is just 1. I'm integrating 1 over 2 pi times the integral from negative pi to pi of 1. Well, what is that going to give me? This is just going to become 2 pi over 2 pi. This is just going to become 1. You can see now why we added this particular scalar to our inner product for this space. Now, in general, if I'm not looking at this in terms of that, if I have, for example, something else that I want to integrate, then we can go through and check that the integral of cosine of like some value, I won't call it m or n, I'll call it kx, plus I times sine of kx, going from negative pi to pi. Whenever I go through and try and integrate this, what ends up happening is that this evaluates to be 0. One way to think of it is that pi and negative pi, in terms of what cosine and sine evaluate to, are all the same. Pi, cosine of pi is the same as cosine of negative pi. Same thing if I were to multiply it times a constant. And that cosine of 3 pi is the same as cosine of negative 3 pi. Same thing for sine. Sine of 3 pi is the same as sine of negative 3 pi. These are all a rotation of 2 pi away from each other. So both of these terms, once integrated, should evaluate to be 0. And since that's the case, we know that this is all going to evaluate to be 0 anytime that m is not equal to n. When m is equal to n, we're in the e to the 0 case, and we know that that evaluates to be 1. Hence, these functions, h0, h1, h2, and in fact, all the ones with negative values too for n, all end up forming an orthonormal set. So these form an orthonormal set inside of this space. One can show, in fact, that this is a maximal orthonormal set inside of this space. What we mean by maximal is that we can't add anything else. There's nothing else that we can throw in this set and say, okay, this set is still orthonormal. Not even orthogonal, in fact. If we were to throw it in and it would stay orthogonal, we could just normalize the element. But nothing else works to get us to that point. We're going to discuss this as an orthonormal basis later on, but we're going to need a little bit more machinery in order for us to get to that point. But this is a big reason why these functions in particular are used to define what is known as a Fourier integral. This is what is known as a Fourier integral. These things form a particular basis of this space, and these trigonometric integrals end up creating wave functions that store information of a function into little parts. And in fact, if you instead of looking at all of the parts of the function, if you look at a small range of the function, what you're doing is known as a kind of like a Fourier compression of a piece of data. And this can give us a neat functional application of orthonormal bases to computing, to signal processing, to a lot of other things that allow us to save data. Right? So this is one of those types of examples here. Now, one of those pieces of information, that's machinery that I was talking about before, is that we still haven't proven that orthogonal implies that the vectors are linearly independent. You might notice that from all of our R3 or Rn examples that seemed to follow pretty quickly, right? We were looking at vectors like 1, 0, 0, 0, 0, 1. These things are going to be linearly independent from each other, but we want to do this in a general context as well. There's nothing in the definition that seems to imply this to be immediately true. But let's start by taking some non-zero vectors that are orthogonal, and let's assume that there is some sort of linear combination that makes them 0. Remember that linear independence means that I want to show that each of these constants is indeed 0. The only way to solve this equation is trivially, if all of the constants here are 0. So that's what we're trying to get toward. So here's what we're going to do. We're going to try and take an inner product of this vector t1v1 plus dot 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 plus tkvk with each of the individual vectors v1 through vk, and we're going to see what we come up with. We're going to see what we come up with. So what we're going to start with is take this vector here and take its dot product with vi. Well, what do you think is going to happen? Inner product is linear in the first variable, so I can take out the scalars, I can break apart each of the terms, and I'm left with a bunch of stuff. a bunch of terms that are either, say, let's take a look at them. Things like v1, vi times a t1 plus t2, v2, comma, vi, and so on and so forth. So I get a lot of terms that look like this. Well, first things first, I know that this whole term is equal to 0. So this whole inner product is going to be equal to 0. Now, secondly, I know also that I can, once breaking it apart, write this whole thing, get that thing is equal to 0, and that a lot of these terms individually equal 0, everything except the ith term. So the only thing that this is going to be left once I cancel out all the terms that just evaluate to give me 0 here is going to be ti times the inner product of vi with itself, which is just, by the way, non-zero, since these are non-zero vectors. Well, if this is equal to 0, then, well, this is not equal to 0, so ti must be 0 then. Since we can do this for any vector vi and let I range from 1 to k, we get that t1 and t2 and tk and all of the elements in between, all of these are equal to each other, and they all equal 0. Because of that, we have that this is indeed the trivial equation here. So this shows that orthogonal vectors, and whenever they're plugged into the linear independence relationship, we can show that they indeed are linearly independent. The only solution here is the trivial one. Now let's get to talking about an orthonormal basis. Let's suppose we have an orthonormal set that also forms a basis for this inner product space. An example to be looking at is the previous one we were looking at, the continuous functions going from negative pi to pi into the complex numbers. And let's say that we write any two vectors in terms of this orthonormal basis. It's a basis, so we can do this for any two vectors inside of our inner product space. Well, let's talk about our inner product a little bit. Turns out that our inner product of these two things looks a little bit like a dot product whenever it's written with respect to this basis. An example to be thinking of here is going back to Rn. We could think about our orthonormal basis as being like 1, 0, 0, 0, 1, 0, and 0, 0, 1, an orthonormal set that is also a basis. And now, if I want to write any vector in terms of this basis, like 3, 5, 4, for example, what am I doing? Well, I'm just breaking this apart into 3, 5, and 4. Those are the scalars that I'm writing with respect to each of those basis elements. And then what am I taking to make the inner product of 3, 5, 4 with another vector? I'm just writing it like this. I'm just taking it and taking the scalars, putting them apart. That's the dot product. It turns out that if you have an orthonormal basis for a generic inner product space, then you can write the inner product in the same sort of way with respect to these two things. Notice the bars on top of y1 through yn, because we could be looking at a complex vector space here, a vector space over the field C. And also, we get that the norm of a vector x is going to be the square root of the absolute values of these each of these components of x squared. So the distance formula. So the distance formula now gets recovered here, the Euclidean distance formula, from looking at this inner product. 2 is going to follow from 1, by the way, and that's because if I just take the inner product of x with itself, I'm going to get x1 times x1 bar. That is x1 absolute value squared. And then to take the norm of that vector, I'm going to need to take the square root of both sides. And so that is where 2 is going to come from. Now, in general, how do we show this? Remember that inner products we don't know very much about. We know that they are linear in both variables, though, and that's exactly what we're going to be using. We're going to start by writing x as a sum in terms of each of these orthonormal basis elements, so something like this. And we're going to start by taking out the sums of the scalars from the first term. When we take out the sums and scalars from the first term, remember that the inner product is linear in the first variable, so the sums and the scalars just come out as they are, but it is conjugate linear in the second variable. That means that the sum can come out just fine, but the scalars need a bar above them, right? So we have this as everything once everything comes out. Notice the sums and the scalars are both out, and all we're left with is vi comma vj. Well, what do we know about vi comma vj? This is 0 whenever I is not j, and it is equal to 1 when I equals j. So here's what happens. You take a look at all of these elements. X sub I, bar y sub j, and you say which ones are 0. Well, the ones that are going to be 0 are say for a fixed I, all of the terms j where I is not equal to j. So what I can do is I can compress these two sums into one, because if I evaluate this term in here for all j, given a fixed I, like before, then there's actually only one term left standing. There's only one term that is non-zero inside of this inner sum, and it's going to be the one where j equals I. So it's going to be the one where j becomes I. You can see here with this way of writing it, y sub j became y sub I right here. Okay. Just kind of clear this up a little bit. So x sub I times y sub I bar, and you'll notice that the inner product of v sub I with itself has disappeared, and that's because that's equal to 1. It's just 1 times that. So everything becomes the dot product formula. Right? Once we have our orthonormal basis of our vector space, it becomes a lot easier to compute as long as we can write things as coordinates inside of that orthonormal basis. So having an orthonormal set that serves as a basis is very important for our vector spaces here, because it allows us to write inner products as, well, in this way that's similar to a dot product in Rn. But that will do it for us today. So that gets us through orthonormal and orthogonal sets and bases in these more generic sets. And the question is how are we going to be generating these sorts of things? Next time, we're going to be talking about a construction of how to create orthogonal or orthonormal bases. But that'll do it for us today. Thank you so much. Have a wonderful day.